Welcome to this explainer. Today we're taking a concept you hear literally everywhere, artificial neural networks, and we're going to break it down into a clear, completely logical engine of learning. We hear terms like machine learning and neural nets thrown around every single day, right? Usually surrounded by a ton of hype. But today we're stripping all that mystery away. We're going to look under the hood and really understand the exact mathematical heartbeat that powers these incredible systems.
So, first things first. We really need to get past this idea that AI is just, magic. It's not. To truly wrap our heads around this technology, we have to start by answering one incredibly fundamental question. How does a piece of silicon and code actually learn anything? Well, think about how we learn. Human beings learn through experience, trial, and a whole lot of error. And as it turns out, the most powerful computer systems in the world learn in a remarkably similar way, using a structure designed specifically to mimic our own biology.
All right, at its core, an artificial neural network, or ANN, is really just a computational system that takes its inspiration right from the biological neurons in the human brain. The whole idea here is to build a massive system of interconnected artificial neurons that can independently learn patterns from raw data. And the absolutely crucial takeaway here is that it doesn't just memorize things, it learns by constantly adjusting its own connections based on the errors it makes. It finds complex patterns that are honestly just way too numerous for a human programmer to ever write out manually.
Here is our roadmap for today's explainer. We'll start with the anatomy of a neural network, then look inside the artificial neuron, break down the machine learning cycle, explore advanced network architectures, and wrap things up with real-world neural networks.
Okay, let's jump right into Section 1, Anatomy of a Neural Network. So every basic neural network is built on three main components: an input layer, one or more hidden layers, and an output layer. Think of a bank trying to predict customer churn, basically figuring out if someone is going to close their account. The input layer takes in the raw features, right? Things like a customer's age, their credit score, their current balance. Then, the hidden layers sitting in the middle take over, performing these complex mathematical transformations to pull out hidden patterns from that data. Finally, all that deeply processed information converges at the output layer, which hands us the final prediction. Is this customer going to stay, or are they going to leave?
Moving right along to Section 2, inside the artificial neuron.
Now, if we zoom in on the hidden layers, we find the basic computational unit of our network, the artificial neuron. Every single neuron receives inputs from the previous layer, but it doesn't just blindly pass them along. No, each connection has what we call a weight, which determines exactly how strongly that specific input should influence the neuron. A large weight basically means, hey, this input is super important. The neuron multiplies the inputs by their weights, adds a little extra threshold value we call a bias, and calculates a weighted sum. That result is then transformed into an activation value, and that is what gets passed to the next layer.
To actually make sense of all that math, neurons use these things called activation functions to transform the data before passing it forward, and there are several types, depending on the job at hand. For example, Sigmoid converts inputs into a value between 0 and 1, which is absolutely fantastic for representing probabilities. Then you have ReLU, or rectified linear unit, which simply turns any negative number into a 0. You'll see this everywhere in hidden layers. And Softmax is just brilliant for the final output layer because it takes a bunch of raw scores and cleanly converts them into a probability distribution that perfectly adds up to 100%.
Which brings us to Section 3, the machine learning cycle.
This is where the whole thing comes to life, though. As we've seen, it's still just math. We start by initializing those weights with small random numbers. Then we push our data from left to right through the network in a process called forward propagation to actually make a prediction. Next, we use a loss function to calculate the error, basically comparing the network's prediction to the actual true answer. Finally, we do backpropagation. Think of a student taking a practice test. Forward propagation is taking the test. The loss function is the red ink grading it. And backpropagation, that's the student studying exactly what they got wrong so they can update their knowledge for next time.
Let's actually put some numbers to this forward propagation idea. Imagine our network takes in raw data, processes it through those hidden layers using functions like ReLU and Sigmoid, and hits the final output layer. Using the Softmax function, it gives us a really clear probability distribution. Let's say there are three possible classes. It assigns a 14.20% probability to class 1, a 47.17% probability to class 2, and 38.62% to class 3. So looking at that, the network is heavily favoring class 2 as its absolute best guess.
But of course, when we compare that best guess to the actual true answer, we see it's not quite perfect. The real answer is that class 2 is definitively correct, which we'd represent mathematically as a 1.0, with zeros for the other classes. But our network only guessed 0.4717. That gap between the prediction and the reality, that is our loss. And this exact specific measurement of error is what triggers backpropagation, sending a signal backward through the entire network to tweak and fix its internal weights.
Now, the network obviously doesn't just do this once. It runs this process over and over. Every single time the network finishes studying its mistakes and retakes the test using the entire training data set, say all 10,000 samples, that one complete pass is called an epoch. And between these epochs, the network relies on something called a learning rate. You can think of the learning rate like a dial that decides exactly how aggressively to study and update those weights. A small learning rate means it's making tiny, cautious adjustments, while a large one means it's taking massive leaps.
All right, moving to Section 4, Advanced Network Architectures.
When we start scaling this up, the simplest version is a single-layer perceptron. It literally has no hidden layers at all. It just connects inputs straight to outputs. Great for super simple, linear problems, but let's be real. Real life is rarely simple. That's exactly why we use multi-layer perceptrons, or MLPs. These bad boys have multiple deep hidden layers to tackle highly complex, non-linear problems. And to keep these massive networks from just lazily memorizing the training data, which is a huge problem called overfitting, they use brilliant techniques like dropout. Dropout temporarily turns off random neurons during training, basically forcing the network to learn genuinely robust patterns rather than just memorizing the answers.
There's also a major difference in how data actually flows through these architectures. Up to now, we've mostly talked about feed-forward networks, where information pushes in a straight, one-way street from the input layer directly to the output. No loops. But then you have feedback networks. In a feedback network, information is actually allowed to flow backwards. This creates these recurrent loops, meaning the network can essentially retain a memory, allowing previous information to influence future processing. That is absolutely vital for context-heavy tasks like processing human language or speech.
And finally, Section 5, Real-World Neural Networks.
So why does all this matter? Well, because this exact mathematical loop is running behind the scenes of our daily lives right now. As we speak, a bank is using these very networks to look at customer tenure and credit scores to predict if you have an 82% or a 15% chance of taking your business elsewhere. In the medical field, these same multi-layer architectures are processing medical scans to successfully detect cataracts. From flagging a fraudulent credit card swipe in milliseconds to powering the natural language processing in your smart speaker, the applications are literally everywhere.
Ultimately, AI really isn't a mystery. It's not science fiction. It is just a relentless, highly efficient mathematical loop. You initialize random weights, you feed input data forward to make a guess. You calculate the loss to check the error. You use backpropagation to adjust the weights, and you repeat the whole shebang across hundreds of epochs until the model learns a highly accurate mapping of reality. Guess, check, adjust, repeat. That's it.
Which leaves us with a pretty fascinating final thought for this explainer. We've seen that these systems are essentially massive engines of trial and error. But if these machines learn exactly like we do, by rigorously studying their own failures and minutely adjusting their internal connections to be just a little bit better the next time, how complex are the problems they'll eventually be able to solve? I mean, are there any real limits to a system that literally never gets tired of learning from its mistakes? Thank you so much for joining me today, and keep exploring.